Welcome back to Mechanical Engineering Made Simple, part 2 of our 5-part series on fluid mechanics. Textbook theory assumes everything flows in nice, clean order. Reality runs on pure chaos, just like everything else in life. Laminar is the lie you start with. Turbulence is the truth you end with. So when your pipes start acting up at 3 a.m. like that crazy X, just remember, school gave you pretty streamlines and polite equations. The real world brought vibration, rough walls, heat, and pressure spikes. Fluid mechanics isn't complicated, it's just honest. Hit like and follow, drop a comment if you enjoy the episode.
I love that intro. It really sets the stage for, well, the reality of what we do.
Thanks. Yeah, and that honesty is exactly why we're doing this deep dive today. We're on a mission, you know?
Oh, absolutely. A mission to bridge that gap.
Right. We want to take those pristine, perfect equations you see written on a whiteboard in some, university classroom, and we're dragging them kicking and screaming into the messy, chaotic reality of the industrial world.
Which is exactly where they belong.
Yeah. So our goal for today's class is to break down the biggest real-world issues you all keep running into out in the field. We're going to call out the common misconceptions that lead to, honestly, catastrophic failures. And we'll answer the most popular questions you are asking online about fluid behavior.
It's a critical transition to make. Frankly, it's where engineering becomes almost an art form.
An art form? Really?
Yeah, I mean, because when you're sitting in a classroom, you are dealing with this idealized universe. You assume the fluid is perfectly behaved.
Right, like the math just works out neatly.
Exactly. You assume the pipe is geometrically perfect, and that time essentially stands still so your calculations balance.
But the real world doesn't care about our neat little math problem.
Not at all. The moment that fluid enters a heavy hydraulic machine or a massive cross-country pipeline, it stops being polite.
Yeah.
The physics gets incredibly complex, incredibly fast.
And if we don't adjust for that, things break.
Big time. We have to rethink our entire approach to fluid behavior when it leaves that theoretical space. Ignoring the reality of the fluid is exactly how you end up with shattered pipes, destroyed heat exchangers, and, million-dollar systems that just mysteriously fail to hit their performance specs.
Okay, let's unpack this. I want to start with the fundamental way fluids move and interact with themselves. Let's look at the first big lie we tell ourselves when we start engineering a system.
I think I know which lie you're talking about.
Probably. But before we get to the lie, let's set the table. We all know the basics, right? Liquids are tough to compress, they have a free surface.
Right, and gases are highly compressible
Yeah.
and expand to fill whatever container you shove them into.
Exactly. But the real magic, the thing that dictates how a system actually performs, comes down to viscosity. The fluid's internal resistance to flowing.
Yeah, the friction of the fluid rubbing against itself.
Right, and there is a classic visualization for this called Couette flow, right?
Yes, Couette flow. It is the perfect mental model to understand viscosity because it strips away all the complexity of a round pipe.
It just looks at the pure shearing action, right?
Exactly. Imagine two completely flat, parallel metal plates. The space between them, maybe a gap of just a few millimeters, is filled with a fluid. Let's say it's oil.
Okay, so a thin layer of oil between two plates.
Right. Now you bolt the bottom plate to the floor, so it is perfectly still, and you start dragging the top plate horizontally at a constant, steady speed.
So I'm basically sliding one plate over the other with the oil acting like a slippery sandwich filling.
That's a great way to picture it. Now, if we could zoom into the molecular level, we'd see something fascinating. The layer of oil molecules immediately touching the bottom stationary plate, it doesn't move at all.
Wait, not at all.
Not even a little.
So-
It has zero velocity relative to that plate.
Mhm.
It essentially locks onto the metal surface due to intermolecular forces.
Oh, right.
This is a fundamental concept we will come back to later called the no-slip condition.
Okay, so the bottom layer is stuck.
Yes. Conversely, the very top layer of oil molecules locks onto the moving top plate, traveling at the exact same speed as that plate.
So the bottom is stopped, the top is moving fast. What is happening to the oil in the middle?
It creates a velocity gradient. It forms this straight diagonal line of increasing speed from the bottom to the top.
Like a staircase of fluid?
Sort of.
Hmm.
Imagine the fluid is made up of thousands of microscopic, horizontally stacked sheets of paper. The top sheet moves fast, dragging the sheet below it slightly slower.
Which drags the sheet below that slightly slower still all the way down to zero.
Precisely. The force it takes to drag that top plate to overcome the friction between all those sliding sheets of fluid is your shearing stress.
And how much force is required depends entirely on the fluid's absolute viscosity.
Exactly.
And if we map out that relationship between how hard we pull and how fast the fluid shears, we get into Newtonian versus non-Newtonian fluids.
Yes, the classic divide.
For things like water, air, or standard lubricating oil, they're Newtonian. That means the relationship is perfectly linear.
Right, the shear stress is directly proportional to the velocity gradient.
So if you push them twice as hard, they move twice as fast. They are predictable, reliable, and mathematically friendly.
They follow Newton's law of viscosity to the letter. But, the industrial world isn't just pumping pure water.
Far from it.
Right. We pump liquid pulp in paper mills. We pump raw asphalt. We pump drilling muds, high molecular weight polymer solutions, chemical slurries.
And those do not play nice.
No, they don't. These are non-Newtonian fluids, and they do not care about Newton's clean linear equations. If you look at a rheological diagram for these fluids, they do wild things.
I always think of Newtonian fluids like a predictable employee. Push them twice as hard, they work twice as fast.
I like that analogy.
Yeah, and non-Newtonian fluids are like a moody artist. Push them hard and they might just turn solid to spite you.
Yes, like a shear thickening fluid where the harder you hit it, the more viscous it becomes.
Like cornstarch in water.
Oobleck, right. Exactly. If you stir it slowly, it acts like a thin liquid. If you punch it, it acts like solid concrete.
That stuff is crazy.
It is. Then you have shear thinning fluids, like ketchup or certain types of paint. They are incredibly viscous, almost solid, until you apply a heavy shear force.
Right, like smacking the bottom of the ketchup bottle.
Exactly. At that point, their viscosity collapses and they flow easily.
Which makes a mess on your fries.
Right. And then you have Bingham plastics, like toothpaste or heavy sludge, which act entirely as a solid resisting all movement until you apply a massive initial threshold force.
A yield stress. Right.
Yes, a yield stress.
Yeah.
And only then do they break down and start flowing like a liquid.
Man, it's a nightmare to design a pump for something that constantly changes its own thickness based on how hard the pump is pushing it.
It takes a lot of specialized engineering, that's for sure.
But that brings me to the massive trap I see engineers fall into, the lie I mentioned earlier.
Ah, the incompressible lie.
Yes. The idea that water is completely incompressible. We treat liquids as if their volume is a universal constant, completely immune to pressure.
And that assumption is incredibly dangerous.
Is it really that bad, though?
Well, yes and no. For everyday municipal plumbing or a low-pressure cooling loop, assuming water is incompressible is a perfectly acceptable mathematical shortcut.
Because the change in volume is negligible.
Right. But textbook shortcuts don't survive in high-pressure engineering. If you are working with heavy hydraulic machinery, deep-sea submersibles, extreme pressure injection systems, the fluid's compressibility absolutely must be accounted for.
So liquids actually do compress.
They do compress. They just fight back incredibly hard when you try to do it. We measure that resistance, that stiffness of the fluid, using a property called the bulk modulus.
Okay, I have to push back here on behalf of every mechanical engineering student who just spent 3 semesters canceling out the density variable in their equations because liquids don't compress.
I know, it hurts to hear.
Wait, water shrinks. If I have a massive hydraulic cylinder, the oil inside is physically getting smaller.
It physically gets smaller. The molecules are being forced closer together, compressing the microscopic void spaces between them.
That is wild to think about.
It is. And the consequences of ignoring this are severe. Let's look at the mechanical implications. Say you are designing a precision hydraulic actuator for an automated manufacturing line.
Okay, so something that needs to be super accurate.
Exactly. It needs to extend a robotic arm exactly 3 millimeters to insert a microchip. If you calculate the required fluid volume, assuming absolute incompressibility, you will be wrong.
Because under high pressure, the volume of your hydraulic oil physically shrinks.
Yes, your actuator won't extend as far as the math predicted. The pressure forces the fluid to compress before it forces the piston to move.
Oh, wow. So you'd miss the target completely.
It might only be a fraction of a percent of shrinkage, but at high industrial tolerances, it entirely destroys your precision.
But how much pressure are we actually talking about here? To shrink the volume of water by just 1% at standard room temperature, you need a massive amount of force.
Right? You need roughly 20 million pascals.
Good grief.
Or about 290 atmospheres of pressure to shrink water by 1%.
Okay, that sounds astronomically high to a layperson.
It does. But in heavy machinery, earth movers, high-pressure water jet cutters, or deep well oil drilling operations, you hit and exceed those numbers routinely.
Wow.
And it's not just volume calculations that get thrown off. Compressibility stores energy.
Like a spring.
Exactly like a giant, very stiff mechanical spring. If a valve suddenly fails, that compressed liquid expands violently, releasing all that stored spring energy at once, which blows out seals and shatters casings.
So as an engineer, at what exact point do I have to stop using the easy math?
A good question.
Like, when does a liquid cross the line and force me to account for its compressibility?
It comes down to comparing the speed of the fluid to the speed of sound within that fluid. This ratio is the Mach number.
Mach number, right. Usually hear that with jets.
Right, but it applies to liquids too. When the flow velocity starts approaching roughly zero point 0.3 Mach, or a 30% fraction of the local speed of sound, the compressibility effects become too large to sweep under the rug.
But for liquids, the speed of sound is extremely high, isn't it?
Very high. In water, sound travels at roughly 1,480 meters per second because the molecules are so tightly packed.
So you generally only hit these Mach numbers at extreme pressures.
Exactly, or in highly specialized applications like diesel fuel injectors, where fuel is blasted through microscopic nozzles at insane velocities.
But the threshold exists.
It does. And assuming a fluid is perfectly rigid, just because it's a liquid, is a great way to design a system that tears itself apart.
And that leads us perfectly into the next massive theoretical illusion we have to shatter.
Which one?
The idea that fluids want to flow in polite, orderly lines. Let's talk about the laminar lie and the turbulent truth.
Ah, yes. This is perhaps the most fundamental division in all of fluid dynamics.
Right, because flow exists in two primary regimes.
Yes. Laminar flow is the ideal. It is smooth, it is quiet, and the fluid particles move in nice, straight, parallel streams.
Like a deck of cards sliding over each other smoothly.
Perfect analogy. There is absolutely no lateral mixing. Fluid at the top of the pipe stays at the top. Fluid at the bottom stays at the bottom.
But turbulent flow is the reality of the universe.
Always. It is chaotic.
Yeah.
You have wild lateral motions, swirling microscopic whirlpools called eddies superimposed on the main forward flow, and highly irregular, unpredictable fluctuations in velocity and pressure.
The history of how we mathematically define this is absolutely fascinating.
Osborne Reynolds, right?
Yes. Back in the late 1800s, a Victorian-era engineer named Osborne Reynolds set up this brilliantly elegant experiment in Manchester.
It really was an elegant setup.
He took a long, straight glass tube, connected it to a water tank, and ran clear water through it. Then he took a tiny razor-thin needle and injected a steady stream of highly visible colored dye right into the dead center of the flowing water.
Such a simple but effective visual.
Totally. When the water was moving slowly, the dye formed a perfect, unmoving, thread-like line straight down the center of the tube. It looked like a solid glass wire suspended in the water.
That was pure laminar flow.
Exactly. Because the viscous forces of the water, that internal friction holding the layers together, were strong enough to keep all the water molecules marching in a perfectly straight line.
The dye had nowhere to go but straight forward.
But then Reynolds started opening the valve, he increased the velocity of the water.
And this is where things get interesting.
Right. For a while, the dye line stayed straight. But suddenly, at a very specific speed, that pristine straight line of dye just shattered.
It just broke apart.
It began to vibrate, then it whipped back and forth, and then it mixed violently with the surrounding clear water, instantly turning the whole tube a cloudy, chaotic color.
It was like a switch had been flipped from order to absolute chaos.
What Reynolds discovered was that this transition wasn't arbitrary. It was a battle between two competing forces in the fluid.
Yes, on one side you have inertial forces. This is the momentum of the moving fluid, proportional to its density and velocity, which wants to push the fluid forward but also makes it prone to wandering off course if disturbed.
And on the other side,
You have viscous forces. This is the fluid's internal friction, which acts like glue, trying to dampen out any wandering and hold the layers together.
and he formalized this battle into the most famous dimensionless number in engineering.
The Reynolds number.
Right. It is essentially the ratio of those inertial forces divided by the viscous forces.
Mathematically, it's the fluid's velocity multiplied by the diameter of the pipe divided by the fluid's kinematic viscosity.
So if the Reynolds number is low, viscosity wins, the fluid acts like thick syrup, and you get smooth laminar flow.
Exactly. And if the Reynolds number is high, inertia wins, the glue fails, and you get chaotic turbulent flow.
And this is where the engineering heartbreak happens, because we absolutely love laminar flow. We desperately want our systems to operate in the laminar regime,
We really do.
because the pressure drop is drastically lower, right?
Yeah. Yes. The friction is manageable. It requires significantly less pumping power, which means smaller pumps, less electricity, and millions of dollars saved over the life of an industrial plant.
But in real-world industrial pipes, flow is almost always turbulent,
Almost always.
which brings up a massive area of confusion I see online. A lot of textbooks and professors will hand you a single hard number. They will declare authoritatively that if the Reynolds number is below 2,320, the flow is laminar.
Right.
And if it is above that, it is turbulent. They treat it like a hard border crossing.
And that is a gross oversimplification. 2,320 is generally accepted as the lower critical limit.
Meaning what, exactly?
Meaning, below that number, viscous forces are so dominant that even if you intentionally violently stir the water before it enters the pipe, the fluid will eventually calm itself down and return to a laminar state.
So the viscosity dampens out the chaos.
Exactly. But the upper limit, the point where a perfectly smooth flow must become turbulent, that limit is almost infinitely elastic depending on your laboratory conditions.
Hold on, so it's not a hard rule. If I have a Reynolds number of, say, 10,000, I could theoretically still have smooth, glassy, laminar flow.
Theoretically, yes. An experimenter named Ekman actually managed to keep flow completely laminar up to a Reynolds number of 50,000.
Wait, 50,000?
Yes.
How is that physically possible to push the math that far past the breaking point?
By creating a completely artificial, hyper-isolated environment. Ekman had to ensure the upstream water in the supply tank was perfectly, absolutely still.
Like no vibrations at all.
None. Left to settle for days so not a single convection current remained. The entrance to the glass tube had to be geometrically flawless, with a perfectly flared bell mouth to prevent the slightest separation.
That sounds intense.
He even isolated the entire apparatus from the microscopic vibrations of the building itself. If you remove absolutely all external disturbances, the viscous forces can miraculously hold the laminar layers together under immense velocity.
But I'm guessing it's a super fragile state.
Hyperfragile state.
Yeah.
At a Reynolds number of 50,000, the fluid is practically screaming to become turbulent. The moment a microscopic vibration, a truck driving by outside, a tiny temperature gradient hits the system, the inertial forces seize upon that flaw, and the flow flashes into violent turbulence instantly.
A great everyday visual for this fragile transition is a lit cigarette resting in an ashtray in a perfectly still room.
Oh, that's a brilliant example.
Yeah, the smoke rising from the cherry is incredibly hot, so it accelerates upward. For the first few inches, it rises in a pristine, perfectly straight blue ribbon, laminar flow.
Because the Reynolds number is still low.
Right, but as it accelerates, the Reynolds number increases, inertia builds, and suddenly, for seemingly no reason, that straight ribbon buckles, folds, and breaks into a wavy, swirling, chaotic cloud of gray smoke.
The microscopic air currents in the room finally trip the fragile laminar balance into turbulence.
Exactly. Here's where it gets really interesting, though. If laminar flow is so incredibly efficient and saves us millions on pump sizing, why can't we just engineer our way out of this?
What do you mean?
Look, why can't I just manufacture an ultra-smooth, perfectly polished titanium pipe, isolate my pumps with rubber dampeners, and force the fluid to stay laminar even at high velocities?
It is a brilliant thought experiment, but the universe simply won't allow it because of the fundamental nature of isotropic turbulence.
So they can't beat it.
No, because turbulence isn't just fluid sloshing around. It is a cascade of kinetic energy transferring through a massive hierarchy of swirling eddies.
Okay, walk me through that.
In a turbulent flow, you have large macro eddies the size of the pipe diameter. These are unstable, so they break apart into smaller eddies, which break into even smaller microscopic eddies.
Passing the kinetic energy all the way down.
Yes, until it is finally destroyed by viscosity and turned into heat. This is an inherent property of fluids at high momentum.
So even with a perfect pipe, the fluid itself is the problem.
Exactly. Even if you manufacture a pipe that is atom-perfectly smooth, you cannot control the molecular and thermodynamic perturbations within the fluid itself.
Like tiny heat changes.
Yeah, a tiny fluctuation in the local fluid density, a microscopic variance in heat, creates a microscopic lateral movement. At high Reynolds numbers, the inertial forces are aggressively looking for a reason to break the layers.
They just want an excuse to go crazy.
Exactly. That tiny thermal perturbation amplifies. It trips the adjacent layer, creating a microscopic eddy. That eddy trips the next layer, and suddenly that chaos cascades outward in milliseconds until the entire flow is a turbulent mess.
So you really cannot force a high Reynolds number flow to stay laminar in a macroscopic industrial setting.
The underlying thermodynamics of the universe actively fight you.
Man, that's rough. So ultra-smooth pipes won't save us from turbulence, but talking about the smoothness of the pipe tees us up perfectly for our next massive hurdle.
The wall itself.
Right. Because while we've been talking about the fluid in the center of the pipe, the fluid that is actually physically touching the metal wall is playing by a totally different set of rules. We need to explore the hidden friction boundary layers and flow separation.
This is where things get mechanically punishing. To understand pipe friction, drag on an airplane wing, or why a boat hull needs constant cleaning, we have to define the boundary layer.
Right. Whenever a viscous fluid flows past a solid boundary, a strange physical phenomenon occurs.
Yes. The fluid velocity directly, microscopically adjacent to the wall is absolutely zero. It stops entirely.
This is that no-slip condition you mentioned earlier.
Exactly.
And to be clear, it's not just moving very slowly. It is completely perfectly stationary relative to the pipe.
Completely stationary. The fluid molecules are literally captured by the intermolecular forces and microscopic roughness of the solid surface. So you have a layer of fluid at zero velocity.
But just a millimeter away, the main body of the fluid is rushing past at, say, 10 meters per second.
Right, which means there must be a zone of transition. From that stationary wall, moving outward toward the center of the pipe, the fluid velocity gradually, steeply increases, layer by sliding layer.
Until it finally catches up to the free stream speed of the main flow.
Exactly. That entire transition region of retarded, friction-heavy flow from zero velocity at the wall up to 99% of the free stream velocity is the boundary layer.
And as the fluid travels further down the length of the pipe or further back along the flat hull of a ship, that boundary layer doesn't stay the same size, right? It grows.
It does. The friction reaches further and further out into the main flow, dragging more and more fluid down.
We mathematically quantify this growth using a couple of distinct measurements. There is displacement thickness, which is a brilliant conceptual tool.
It really is.
It essentially asks, because the boundary layer is slowing the fluid down, how much would we have to physically shrink the diameter of the pipe to end up with the exact same reduction in total flow rate?
It represents the mass flow deficit.
Precisely. And then you have momentum thickness, which is similar, but measures the deficit of physical momentum caused by that dragging friction.
To actually calculate the mechanical energy lost to this dragging, the pressure drop or head loss, and the pipe engineers rely on the Darcy-Weisbach equation. It is the gold standard.
What goes into that equation?
It factors in the length of the pipe, the diameter, the fluid velocity, and a crucial variable called the friction factor. To find that exact friction factor for a turbulent flow, we use the Colebrook-White equation.
Which is an absolute mathematical nightmare because it is an implicit equation.
Yes, it is not fun to solve by hand.
The friction factor is on both sides of the equal sign, so you can't just solve it algebraically. You have to guess an answer, plug it in, see how wrong you are, and iterate closer and closer to the truth.
Or you just cheat and look at a Moody diagram like the rest of us.
True. The Moody diagram is a lifesaver. It maps out the relationship between the Reynolds number, the relative roughness of the pipe wall, and the resulting friction factor.
But reading that diagram brings us to a massively counterintuitive reality in fluid dynamics. It's an assumption that trips up junior engineers constantly.
Let me guess. A rough pipe always causes more drag than a smooth pipe.
Exactly.
It feels like common sense. I mean, if I rub my hand over sandpaper, it causes way more friction than rubbing my hand over a pane of glass. So a corroded, rough cast iron pipe should obviously cause more fluid drag than a brand new, polished PVC pipe, right?
Sounds perfectly logical, but fluid mechanics doesn't care about human intuition.
So why is that statement false?
To understand why it's false under certain conditions, we have to pull out our microscopes and look deep inside the boundary layer, specifically at a subregion called the viscous sublayer.
Okay, what's happening down there?
Even if a pipe is experiencing violently chaotic turbulent flow in its center, there is a microscopic layer of fluid directly against the pipe wall that is moving so slowly, so close to zero velocity, that the viscous forces dominate it.
So it remains purely laminar.
It does. This ultra-thin, smooth sheet of fluid hugging the wall is the viscous sublayer.
So I have a chaotic, turbulent storm in the middle of the pipe, but right at the metal surface, there's a microscopic safe haven of perfectly smooth, laminar flow.
Exactly.
How does this explain the roughness illusion?
Because hydrodynamic smoothness is not about how the metal feels to your thumb. It's about how the metal interacts with that sublayer.
Meaning the bumps and ridges?
Yes. A pipe is mathematically considered hydraulically smooth if its physical roughness elements, The
Hmm.
microscopic manufacturing bumps, the pits, the crystalline grain of the metal are physically shorter than the thickness of the viscous sublayer.
Oh, I see.
If those bumps are entirely submerged inside that laminar sheet of fluid, the turbulent main flow never physically sees them.
That is wild.
Right. The chaotic flow just glides effortlessly over the laminar sublayer as if the pipe were made of frictionless glass.
The fluid creates its own protective coating over the rough metal.
Exactly. Physical roughness only increases your pressure drop if the Reynolds number gets so high and the flow gets so violently fast that the viscous sublayer is compressed and thinned out.
And then what happens?
If the sublayer gets thinner than the height of the metal bumps, those microscopic jagged peaks suddenly poke out of the laminar safe haven and penetrate into the chaotic turbulent region.
And the turbulence grabs them.
Yes, the turbulent eddies crash into the jagged metal peaks, causing massive drag. That is the moment of clarity for many engineers. You can have a pipe that feels like gravel to the touch, but at low flow velocities, it acts as perfectly smooth hydrodynamically as polished steel.
I love mapping this out visually. I like to compare the boundary layer to traffic on a massive multi-lane highway.
Go on.
The breakdown lane is the solid pipe wall zero velocity. The lane right next to it is crawling at 5 miles an hour. That is the viscous sublayer moving slow and steady.
Okay, I follow.
The middle lanes are going the speed limit, and the far left lane is flying at 80 miles an hour. Now, if every single car stayed perfectly centered in their own lane, never merging, that is laminar flow. The only friction is just the slight aerodynamic drag between the lanes.
But highways are never like that.
Never. In reality, a highway is turbulent. Cars are constantly aggressively changing lanes. A slow semi-truck from the right lane merges directly into the fast left lane, forcing the speeding sports cars to slam on their brakes, instantly destroying their forward momentum.
Yes, and conversely.
Meanwhile, a fast car swerves aggressively into the slow right lane and rear-ends someone. This chaotic lateral lane changing transfers momentum back and forth violently. It creates massive overall friction and slows the entire highway down.
And in fluid dynamics, that macroscopic lane-changing friction caused by turbulent eddies smashing into each other is called Reynolds stresses.
That's an exceptionally accurate way to put it.
Those Reynolds stresses, the macroscopic exchange of momentum between layers, are orders of magnitude larger and more destructive to your system's energy than the simple molecular viscous friction found in laminar flow.
But as much energy as boundary layers and Reynolds stresses consume, there is a secondary phenomenon associated with the wall that is a true system killer.
Flow separation.
Yes. The ultimate manifestation of fluid friction. This is when the fluid just decides it has had enough of rubbing against the wall, gives up, and literally tears itself away from the boundary entirely.
Exactly. And it happens when the fluid encounters an aerodynamic enemy known as an adverse pressure gradient.
What does that look like in a pipe?
Let's imagine a fluid flowing smoothly through a pipe.
Hmm.
Suddenly, the pipe expands into a much larger diameter. As the cross-sectional area increases, the laws of conservation of mass dictate that the fluid's velocity must decrease to maintain the same volumetric flow rate.
Right. A wider pipe means slower fluid.
Now, according to Bernoulli's principle, which we will dissect later, if the velocity decreases, the static pressure of the fluid must increase.
Okay, so the fluid is slowing down, but its pressure's going up.
Right, and that means the fluid is now trying to flow forward into a region of higher pressure than the region it just left. It is essentially swimming upstream against a physical wall of pressure.
This is the adverse gradient.
Yes, the main turbulent flow in the center of the pipe has enough kinetic momentum to smash through that high-pressure wall and keep moving forward.
But the fluid trapped in the boundary layer.
It has already been robbed of its momentum by the friction of the wall. It is exhausted. As it hits that high-pressure gradient, it slows down rapidly. Eventually, the forward velocity of the fluid touching the wall drops to absolute zero.
And what happens when it hits zero? It can't just stay there while millions of gallons of fluid are pushing behind it.
It doesn't.
Yeah.
Because the pressure downstream is now higher than the pressure at the stagnation point, the fluid actually reverses direction. It starts flowing backward along the wall.
Oh, wow.
When this backward-flowing boundary layer collides with the forward-flowing boundary layer coming from upstream, the fluid has nowhere to go but violently inward, away from the wall. It physically tears itself off the metal boundary.
And when it separates, it doesn't leave a vacuum. It creates massive energy-sucking eddies and swirling vortices in the empty space behind the separation point.
It's extremely destructive to efficiency.
It's exactly like tailgating a massive semi-truck on the highway.
Back to the highway.
Always. The flat front of the truck punches a blunt hole in the air. The airflow simply cannot make the sharp 90-degree turn around the back corners of the trailer, so the flow separates. It leaves this massive, low-pressure wake of swirling, chaotic air right behind the truck doors.
And you can feel that, right?
Oh, yeah.
Yeah.
If you are tailgating in your car, you actually feel your vehicle get sucked forward into that low-pressure wake. In a pipe system, whether it's a sudden expansion or an elbow joint, those separation wakes act like black holes for mechanical energy.
They completely tank your system's efficiency and force your pumps to work twice as hard to maintain flow.
But here is where we need to shift gears. Friction, boundary layers, and separation are all about the fluid dragging against the pipe while it is actively moving.
Right.
But what happens when the fluid suddenly stops moving entirely? What happens when all that moving mass essentially throws a punch at the pipe itself? That brings us to the terrifying phenomenon of unsteady flow and water hammer.
Up until this point in our discussion, we have been existing in a state of steady flow.
Which is the nice, polite textbook version.
Exactly. Steady flow is the bedrock of most engineering calculations. It means that if you pick a specific coordinate point in your pipe system, the conditions at that exact point, the velocity of the water passing through it, the static pressure, the density, do not change as time ticks forward.
It is a constant, stable state of operation.
Unsteady flow, on the other hand, means those parameters are actively, dynamically changing over time. And the most dramatic, destructive, and sudden example of unsteady flow is water hammer, or as it's known academically, hydraulic shock.
Let's visualize this. Picture a long, straight steel pipe carrying a massive volume of water at a high velocity. At the very end of this pipe is a heavy mechanical valve.
Okay.
If you take a lever and suddenly slam that valve shut in a fraction of a second, the water directly, immediately behind the valve gate hits a literal brick wall. Its velocity abruptly drops from 10 meters per second down to absolute zero in an instant.
But water has mass. Tons of it.
And because it was moving, it possessed a massive amount of kinetic energy. By the fundamental laws of thermodynamics, that massive kinetic energy cannot just be deleted from the universe. It has to be conserved.
And because it can no longer exist as the energy of motion, it is instantaneously converted into the energy of compression. You get a massive, localized, violent pressure spike right at the face of the closed valve.
Like the fluid just crumples into itself?
Exactly. The water molecules physically crash into each other, compressing slightly, and the steel pipe wall expands outward microscopically under the immense strain.
And the trap, the reason this causes billions of dollars in industrial damage every year, is that standard fluid equations like Bernoulli's assume steady flow.
They don't account for the sudden stop.
Right? Engineers will painstakingly draft their system, perfectly size their pipe diameters, carefully select their wall thicknesses, and choose their flanges and fittings based on the steady-state continuous operating pressure of the main pump.
They look at the CAD model and say the pump outputs 100 psi, the pipe can handle 150 psi, we are perfectly safe.
And they completely forget to account for the dynamic, split-second spikes caused by unsteady flow events like a valve closing.
Because that pressure spike doesn't just sit peacefully at the valve waiting to be relieved. It is a kinetic event. It becomes a shock wave.
Wait, a literal shock wave, like an explosion.
Exactly like an acoustic explosion. That high-pressure wave of compressed water and expanded pipe wall travels backward through the pipe system, moving away from the closed valve and upstream toward the source.
Wow.
And it travels at the speed of sound within that specific fluid. As we discussed earlier, for water, that shock wave is blasting backward at roughly 1,480 meters per second.
That is incredibly fast.
It acts like a physical bullet blasting through the system. It hits elbows and tries to straighten out. It reflects off pumps, T's, and supply reservoirs, bouncing back and forth down the length of the pipe at supersonic speeds until fluid friction and the structural yielding of the pipe finally dampen the energy.
And if the pipe isn't rated for that?
If the pipe schedule or the threaded fittings are only rated for the steady-state pump pressure, that supersonic pressure wave will literally rip the steel open along the weld seam or instantly blow the bolts right off a flange.
Okay. This explains so much about everyday life. Is this exactly why my house pipes violently bang and shudder inside the drywall when my washing machine abruptly stops filling with water?
That is precisely the physics at play. Your washing machine and your dishwasher use what's called a solenoid valve.
Okay, what does that do?
It is an electromagnetically actuated valve that doesn't screw shut slowly like a garden hose. It snaps shut almost instantaneously. When it actuates, the water flowing vigorously through your entire house plumbing suddenly hits a wall.
Creating that same pressure spike?
Yes, the pressure spikes, and the acoustic shock wave slams backward into your copper pipes. The spike is so forceful, it physically causes the pipes to jump and bang against the wooden joists inside your walls.
That startling hammering noise is domestic water hammer.
Exactly.
It is crazy to think about a supersonic shockwave bouncing around inside the walls of my suburban house. But scale that up, what happens when this hits heavy industry?
If we connect this to the bigger picture, imagine that exact same phenomena, but in a hydroelectric dam.
Oh boy.
You have a massive concrete and steel penstock pipe, maybe 10 feet in diameter, carrying thousands of tons of water rushing down a mountainside straight into a spinning turbine.
That is a lot of kinetic energy.
If the electrical power grid suddenly drops the load, maybe a transmission line trips, the turbine loses its magnetic resistance and will instantly overspeed and destroy itself.
So we have to shut off the water immediately.
Right. Massive mechanical valves must close to cut off the water supply to the turbine. But if you close those massive valves even a second too fast, the kinetic energy of a literal river of water is converted into a pressure transient.
The water hammer would be unimaginably violent.
It could obliterate the steel penstock, blow apart the powerhouse, and threaten the structural integrity of the dam itself.
So how do engineers deal with this? We can't just leave valves open forever. We obviously still have to shut down turbines and turn off washing machines.
The primary, most mathematically elegant solution is simply altering the timeline. You must close the valves slowly.
Just buy some time.
Yes. If you engineer the actuator to extend the closure time, a fascinating wave cancellation occurs. The initial pressure wave travels up the pipe, hits the open reservoir, and reflects backward as a low-pressure relief wave.
Oh, I see where this is going.
If the valve is still slowly closing by the time that relief wave returns, the returning low pressure effectively cancels out the building high pressure. The energy is allowed to dissipate safely and gradually.
But what if system requirements demand a fast emergency closure, like a real emergency?
Then you have to engineer physical pressure relief mechanisms into the architecture. In hydroelectric plants, they build massive surge tanks.
What are those?
They are giant, vertical, open-topped concrete towers connected to the penstock. When the valve slams shut, the high-pressure water has a path of least resistance. It simply surges upward into the open tower, trading its kinetic pressure energy for potential height energy, completely buffering the shock.
That makes perfect sense. What about smaller systems?
In smaller industrial settings, we use hydraulic accumulators, which are heavy steel tanks containing a rubber bladder filled with pressurized nitrogen gas. When the water hammer hits, the incompressible water forcefully compresses the gas bladder, acting like a giant pneumatic shock absorber.
Okay, so water hammer is a violent, destructive vibration caused by the sudden shift of fluid momentum inside a pipe. But fluids moving on the outside of structures cause their own unique, terrifying brand of chaos.
Oh, definitely.
This brings us to a massive crossover between fluid dynamics and structural engineering. Let's look at when the fluid strikes back, flow-induced vibrations.
This is where we see some of the most spectacular engineering failures in history. When a fluid, whether it is water or wind, flows around a solid structure, it fundamentally alters the structure's physical vibrational characteristics.
Does sitting water do this too?
Actually, no. A quiescent fluid, meaning a fluid that is just sitting perfectly still around a structure, like a bridge piling in a calm, unmoving lake, actually helps. The mass of the still water couples with the structure, decreasing its natural resonant frequencies and increasing its damping. It acts like a heavy blanket.
But a flowing fluid?
A flowing fluid introduces active, dynamic, and highly destructive mechanical forces. We categorize these aerodynamic forces into a few distinct types: added mass effects, inertial coupling, and the absolute most notorious system killer of them all, vortex shedding.
We talked briefly about wakes earlier, with the semi-truck tailgating analogy causing flow separation. Vortex shedding takes that separation and weaponizes it.
That's a good way to put it.
Let's dig deeper into the mechanics. This phenomenon primarily happens when a fluid flows past what we call a bluff body. A bluff body is an engineering term for any unstreamlined, aerodynamically blunt shape.
Like a cylinder or a square beam?
Exactly. A perfectly round cylinder, a square concrete beam, a hexagonal sensor probe. These are all bluff bodies. Because they aren't shaped like an airplane wing, the fluid simply cannot follow the sharp curves of the geometry, so the boundary layer violently separates.
But it doesn't just form a steady, continuous pocket of dead air.
No. The sheer layers of the separated fluid are highly unstable. They curl back in on themselves and form vortices, spinning whirlpools of fluid that physically peel off the back of the object and travel downstream.
And the critical detail here is that they do not peel off randomly. Once the flow reaches a Reynolds number greater than about 50, these swirling vortices begin to shed alternately from each side of the bluff body in a highly regular, perfectly rhythmic, predictable pattern.
First one side, then the other.
Yes. First, a vortex gathers and sheds from the left side of the cylinder. Then a vortex gathers and sheds from the right side, then the left again, then the right. This beautiful alternating trail of spinning fluid is called a von Karman vortex street.
Now we have to look at the pressure mechanics of that. The fluid inside a spinning vortex is moving extremely fast, which means the pressure inside the vortex drops significantly.
Right.
Therefore, every single time a vortex sheds off one side of the structure, it creates a localized low-pressure zone that literally sucks the physical structure toward it.
This creates an alternating lift force perpendicular to the flow.
Yeah.
Left, right, left, right. The solid structure is being rhythmically, relentlessly pulled back and forth by the fluid.
And it's not just a random pulsing, it's a measurable mathematical frequency. We can actually calculate exactly how fast those alternating pulls will happen using a dimensionless parameter called the Reynolds number.
Yes, the frequency of the shed vortices, measured in hertz, is equal to the Reynolds number multiplied by the flow velocity of the fluid, divided by the physical width or diameter of the object facing the flow.
So if the water flows faster, the alternating pulling gets faster.
Which brings us to the absolute nightmare scenario for chemical and mechanical engineers: fluid elastic instability, particularly as it pertains to tube and shell heat exchangers.
Oh, I've seen the aftermath of this. It's ugly.
It really is. Imagine a massive industrial cylinder filled with a dense array of hundreds of thin metal tubes. You have a hot fluid flowing inside the tubes and a cold fluid flowing across the outside of the tubes to transfer heat.
Standard heat exchanger setup.
As the cross-flow velocity of that cooling fluid increases, you get alternating vortex shedding on every single one of those hundreds of tubes.
But if you push the pump too hard and hit a specific critical velocity threshold, something terrifying happens.
Yes, the vibration amplitude of the tubes doesn't just increase linearly with the flow speed. It spikes exponentially, usually proportional to the flow velocity raised to the power of 4 or even higher.
The vibration becomes so insanely violent that the metal tubes physically bow outward and clash into each other, denting, rupturing, and destroying the metal.
Or they vibrate so hard against their support baffles that they literally guillotine themselves and shear right off.
You noted from the research papers that this fluid elastic instability is the second leading cause of catastrophic heat exchanger failure globally, right behind long-term chemical corrosion. It destroys equipment in hours.
Hours. And there is a highly persistent, incredibly costly trap that structural engineers fall into here.
What's the trap?
When they see a structure vibrating violently in the wind or water, their immediate intuition is, the structure is too weak. I just need to make the structure stronger, stiffer, and weld more heavy steel to it to resist the fluid. They operate under the assumption that structural stiffness implies aerodynamic immunity.
But the aha moment here, the thing that changes how you view structural engineering forever, is realizing it is not a one-way street. It is a closed feedback loop.
Precisely. If the physical structure is even microscopically flexible, and all materials are, the alternating lift forces from the vortex shedding will cause it to physically deflect and move.
And that movement matters.
Massively. That structural movement physically alters the boundary layer of the fluid flowing over it. The motion of the structure begins to dictate and organize the shedding frequency of the vortices.
Wait, so the structure is now controlling the fluid?
Yes. If the calculated natural shedding frequency of the vortices happens to lock on to the inherent resonant natural frequency of the physical steel structure, you achieve catastrophic resonance.
They sync up.
The fluid and the structure synchronize perfectly. Every push from the fluid happens at the exact perfect millisecond to amplify the sway of the building. The displacements become violent.
And making it stiffer doesn't help.
Building a stiffer, heavier structure might just give it a higher natural resonant frequency. This means it won't vibrate at low wind speeds, but it will still violently resonate and tear itself apart, just at a much higher, more dangerous wind speed.
We have seen this play out in the real world with disastrous results. We've seen tall, rigid industrial chimneys and high crosswinds swaying back and forth until the concrete structurally cracks.
We've seen deep water, Offshore oil terminal risers and marine pipelines, subjected to steady ocean currents, vibrating themselves to pieces on the seafloor because of vortex shedding.
So if we can't just arbitrarily throw thicker steel at the problem, how do we actually stop this without completely redesigning the architecture? We can't exactly build a teardrop-shaped, perfectly aerodynamic smokestack.
You have to outsmart the fluid. Instead of attacking the structure's rigidity, you attack the fluid's aerodynamics directly. You have to intentionally sabotage the regularity of the vortex shedding.
Sabotage it.
Because if the vortices cannot shed in a synchronized rhythmic pattern, they cannot organize into a unified resonant pulling force. The poles will be random and cancel each other out.
So how do engineers do that?
Engineers use several clever aerodynamic modifications. The most brilliantly simple and common is the helical strake.
The helical strike, like those spiral fins?
Exactly. If you look at a tall metal smokestack at a power plant, or even something as mundane as the small, rigid spiral fin wrapped around your car's radio antenna, you'll see ridges spiraling up the length of the cylinder.
Those strikes are intentional speed bumps.
They physically force the boundary layer to separate at different times at different heights along the cylinder. The vortices shed completely out of phase with each other, totally breaking up the unified rhythmic force.
Other brilliant solutions include shrouds, which are basically perforated, oversized metal cylinders placed over the inner pipe, or axial slats running straight down the length of it.
Yes, all of these tools share the exact same mission. They are designed to turn organized, rhythmic, resonant aerodynamic pulling into disorganized, random, chaotic turbulence.
In the world of flow-induced vibration, messy, chaotic turbulence is vastly safer than organized harmonic flow.
Exactly right.
So, having covered the sheer mechanical violence of vibrations and supersonic shock waves, we need to take a step back and look at the accounting department of fluid mechanics. How do engineers mathematically balance the books of all this fluid energy?
The energy ledger.
Let's look at the energy ledger Bernoulli and real-world losses.
To understand how energy moves through a system, we have to return to Bernoulli's equation, which is arguably the most famous, heavily utilized equation in all of fluid mechanics.
It's basically conservation of energy, right?
It is fundamentally an expression of the first law of thermodynamics, the conservation of energy applied directly to a flowing fluid. It boldly states that for a steady, incompressible, perfectly frictionless flow traveling along a single streamline, the total energy per unit mass is an absolute constant.
That total energy is essentially a bank account made up of three distinct currencies: kinetic energy, pressure energy, and potential energy.
Let's translate the math into concepts. You have the fluid's velocity squared. That represents the kinetic energy term, the energy of physical motion.
Then you have the static fluid pressure. That is the pressure energy term, the energy of compression.
Finally, you have the physical elevation or height of the fluid relative to the ground. That is the potential energy term, the energy of gravity.
Bernoulli's equation dictates that if you add the balance of those three accounts together at point A at the start of a pipe, they must perfectly equal the sum of those same three accounts at point B at the end of the pipe.
The fluid can freely transfer funds between velocity, pressure, and height, but the total net worth of the fluid cannot change.
And you can see this financial transfer beautifully illustrated in Torricelli's theorem.
Yes, the water tower example.
Imagine a massive, open-topped municipal water tower. Near the very bottom of the tank, there is a small hole. If we look at the very top surface of the water high up in the tank, the water is barely moving downwards, so velocity is essentially zero.
It's open to the air, so the pressure is just zero gauge atmospheric pressure. All of its energy, 100% of its bank account, is tied up in potential energy. It's height above the ground.
As that specific particle of water flows down through the tank and violently squirts out the small hole at the bottom, its physical height is now zero.
The pressure is once again atmospheric because it's shooting into the open air. So where did all that massive potential energy go?
It transferred entirely into the kinetic energy account. The velocity of the water jet shooting out of the hole is exactly the same mathematically as if you had simply dropped a physical bowling ball from the height of the water surface.
It's the ultimate roller coaster analogy. When the roller coaster car is ratcheting up to the very top of the highest hill, it is moving painfully slow. Kinetic energy is minimal, but its potential energy from gravity is at its absolute peak.
As it plunges down the vertical drop, it loses that height but gains massive, terrifying speed. Potential energy converts directly to kinetic energy, which maxes out at the very bottom of the dip where the track is lowest.
Bernoulli's equation says fluids do the exact same thing, just with static pressure thrown into the mix as a third, highly liquid asset.
However, there is a fascinating, highly visible quirk when fluid exits a hole like that, known as the vena contracta.
Yes, the contraction. The streamlines of the fluid inside the tank converge from all directions toward the exit hole. But fluid has momentum. It cannot make a perfect, instantaneous 90-degree geometric turn right at the sharp edge of the hole.
The streamlines literally overshoot the edge and keep curving inward toward the center of the jet, even after they have exited the tank.
This means the actual physical cross-sectional area of the water jet shooting through the air is significantly smaller than the physical area of the hole it just passed through.
The flow contraction coefficient is usually around 0.65, meaning the jet is only 65% the size of the hole.
But Bernoulli's equation, as beautiful and elegant as it is, describes a perfect, frictionless, utopian universe.
And as we have established ad nauseum today, the real industrial world is messy. The massive pain point for engineers sizing pumps here is accounting for what we broadly call head loss.
The energy ledger doesn't actually balance perfectly between point A and point B because the physical universe always takes a tax.
That unavoidable tax is viscous dissipation. As fluid flows through a pipe system, mechanical energy is constantly, irreversibly being destroyed and turned into unrecoverable low-grade heat due to the internal friction of the fluid and the drag against the pipe walls.
We divide these system taxes into two distinct categories for calculation. Major losses, which is simply the friction accumulated along the long, straight lengths of pipe we discussed with the Colebrook-White equation.
And minor losses, which are localized, highly concentrated energy drops caused by the pipe fittings themselves.
And the trap engineers fall into is looking at a massive plumbing schematic and thinking, a pipe fitting is just a piece of metal. An elbow is just an elbow. It just changes the direction. It shouldn't consume that much energy.
But that's a trap.
That assumption will result in a pump that completely fails to deliver the required flow rate. Every single time the fluid is forced to change direction in an elbow, squeeze through the restricted throat of a valve, or navigate a sudden expansion, flow separation occurs.
The boundary layer tears off, violent turbulent vortices are formed, and immense amounts of mechanical energy are burned up simply trying to navigate the geometry.
Different geometric fittings have vastly different, experimentally determined loss coefficients. For example, if a pipe entrance drawing water from a tank is just a sharp, square-cut edge, the fluid separates violently as it tries to turn the corner,
creating a massive vena contracta and extremely high energy loss.
If the pipe physically protrudes inward into the tank, what we call a re-entrant shape, the fluid has to execute a full 180-degree turn to get in. The separation is massive, and the energy loss is even worse.
But if the engineer simply rounds the pipe entrance, giving it a smooth aerodynamic bell-mouth curve, the fluid glides in perfectly without separating, and the localized energy loss drops to almost absolute zero. Geometry dictates efficiency.
We also rely heavily on Bernoulli's energy principles to actually measure flow in the real world. We use pitot tubes, particularly on aircraft, to measure local velocity by bringing the fluid to a dead stop and measuring the difference between the stagnation pressure and the static pressure.
We use Venturi meters and orifice plates inside pipes, which intentionally, physically choke the diameter of the pipe down to force the fluid to speed up. That speed increase causes a measurable pressure drop, according to Bernoulli, which we can then mathematically correlate directly to the mass flow rate.
But actually measuring flow in an industrial setting presents its own unique set of severe challenges, especially when you are dealing with two-phase flows.
Imagine trying to measure an air-water mixture, like the frothy output of a chemical reactor. If you use a standard pitot tube equation calibrated for pure water, but your water has a 20% concentration of entrained microscopic air bubbles, and you naively ignore the compressibility of those bubbles, your velocity calculations will be massively, dangerously wrong.
As the fluid hits the stagnation point of the sensor and the pressure spikes, the liquid water doesn't compress, but the gas bubbles compress dynamically. The density of the fluid mixture changes locally right at the sensor face, skewing the pressure differential completely.
Which provides the absolute perfect runway to launch into our final theoretical concept. We have been mostly talking about liquids today, where we only have to worry about compressibility if we hit extreme, crushing hydraulic pressures, or if we are dealing with entrained air bubbles.
But what happens when the fluid itself is inherently highly compressible? What happens when we push gases to their absolute physical limits? Let's talk about gas dynamics and compressibility.
When dealing with high-speed gases, air, steam, natural gas, almost everything we learned about the predictable behavior of incompressible liquids goes straight out the window.
The primary governing metric here shifts entirely to the Mach number, which, as we noted, is the ratio of the fluid's velocity to the local speed of sound within that exact fluid at that exact temperature.
We strictly categorize flows based on this ratio. Subsonic flow is less than Mach 1. Transonic flow hovers unpredictably right around Mach 1. Supersonic flow is undeniably above Mach 1, and hypersonic flow is generally anything above Mach 5.
And the reason everything changes is density. Unlike water, where a gallon is a gallon, the density of a gas changes wildly and rapidly as its velocity and pressure change. You simply cannot treat density as a constant in your calculus.
And this intense compressibility leads to wild, violent physical phenomena like shock waves. We see normal shocks, which are blunt pressure walls that sit detached and perfectly perpendicular to the flow.
And we see oblique shocks, which form a sharp angle, exactly like the V-shaped Mach cone trailing off the nose of a supersonic fighter jet slicing through the atmosphere.
But bringing this back to terrestrial engineering, the most practical daily hurdle for industrial engineers dealing with gas dynamics is the frustrating phenomenon of choked flow.
Let's do another thought experiment. Imagine you are designing a massive, high-pressure natural gas cross-country pipeline. You have a multi-million-dollar industrial-scale compressor pushing methane gas down a very long, perfectly straight pipe at a steady subsonic speed of, say, 15 meters per second.
As the gas flows down the miles of pipe, wall friction acts continuously upon it. This specific scenario, compressible flow in a constant area duct with friction, is known thermodynamically as Fano flow.
Because it is a compressible gas, the friction dragging against the pipe naturally causes the fluid pressure to steadily drop. But critically, because the pressure drops, the gas expands, meaning its density also drops.
And because the mass flow rate, the actual pounds of gas moving through the pipe per minute, must remain perfectly constant from one end to the other, the gas must actually physically accelerate to make up for its lower density.
Wait, hold on. Let me get this straight. You are telling me that dragging friction, the literal force that slows things down, actually causes the gas to speed up in the pipe.
Yeah.
That feels entirely backwards.
It is entirely counterintuitive to how we interact with solid objects, but it is an absolute thermodynamic truth for subsonic gas flow in a constant area pipe. To maintain the conservation of mass as the gas gets fluffier and less dense due to frictional pressure drop, it has to move faster to push the same amount of mass through the same sized hole.
The velocity keeps steadily increasing as it travels further and further down the pipe.
But it will eventually hit an absolute unbreakable physical limit. As the velocity accelerates and approaches exactly Mach 1, either due to miles of friction along a straight pipe, or because you intentionally force the gas through a narrow bottleneck like a valve, the flow becomes choked.
At the exact microscopic point where the gas velocity hits Mach 1, the laws of physics intervene. No matter how much more pressure you crank out of that million-dollar compressor upstream, the actual mass flow rate of the gas absolutely cannot and will not increase.
If I have a massive compressor, and I crank it to maximum power, dumping megajoules of energy into the system, you're telling me physics just says no. Where does the extra pushing go?
It goes nowhere useful. It just backs up as higher upstream pressure. The fundamental reason is acoustic. The physical information that the compressor is pushing harder upstream communicates itself through the gas via pressure waves.
And pressure waves, by definition, travel at exactly the speed of sound. But if the gas at the bottleneck is already flowing forward at the speed of sound, those pressure waves can never travel backward upstream to tell the incoming gas to move faster. The communication is cut off.
It is exactly like a panicked crowd of 100 people trying to run out of a single set of double doors during an emergency. The people at the very front are squeezing through the narrow doors at their absolute maximum physical capacity.
The people in the back of the room panic and start pushing harder and harder against the crowd. But pushing violently from the back doesn't get people through the front doors any faster. The bottleneck is already maxed out.
The extra pushing just creates a crushing shock wave of bodies in the room. The door is mathematically choked.
A grim but highly accurate physical analogy. And the costly assumption here is treating a high-speed gas pipeline with the exact same math as a municipal water pipe. You cannot just plug your numbers into the standard Darcy-Weisbach liquid friction equations and call it a day.
Thermodynamic effects completely dictate and alter the pressure gradient. As an engineer, you have to precisely determine if the flow is isothermal, meaning it flows slow enough to constantly exchange heat with the surrounding environment and maintain a stable temperature.
Or if it is adiabatic, meaning it flows so fast or is so well insulated that it retains all its frictional heat. The calculated limiting lengths of the pipe and the exact pressures where choking occurs are vastly, fundamentally different depending on that thermodynamic state.
Okay, but this raises a massive contradiction in my head. If flow is completely universally capped at Mach 1 at the tightest bottleneck, how do space rockets ever achieve supersonic speeds? A rocket engine narrows down to a tiny throat to build pressure, so the exhaust gas must choke at Mach 1. How does the thrust ever get past the speed of sound?
This raises an important question, and the answer is arguably one of the most brilliant pieces of mechanical engineering in human history, the de Laval nozzle, or the converging diverging nozzle.
You are correct. You start with a wide combustion chamber and geometrically converge the metal down to a narrow throat. The high-pressure subsonic gas accelerates as it is squeezed, hitting exactly Mach 1 right at the narrowest point of the throat. It perfectly chokes.
But then instead of just dumping that Mach 1 gas into the atmosphere, you attach a carefully machined diverging bell section that slowly widens back out.
Because the gases hit exactly Mach 1, the thermodynamic rules completely invert. In subsonic flow, a widening pipe causes the fluid to slow down. But in supersonic flow, a widening pipe gives the highly compressed gas room to rapidly expand.
The gas density drops incredibly fast, much faster than the geometric area of the nozzle is increasing. Because the density is plummeting, the velocity must violently accelerate to maintain the mass flow rate.
The widening nozzle physically tricks the choked flow into expanding and blasting out the back of the rocket at Mach 2, Mach 3, or even Mach 10. You break the sound barrier not by squeezing harder, but by giving the sonic fluid room to breathe.
Which is absolutely incredibly brilliant. Okay, we have covered a massive amount of theoretical and practical ground today, from the microscopic safe haven of the viscous sublayer all the way up to the thermodynamics of supersonic rocket nozzles. Now it is time to bring it all home to the real world.
Let's do it.
Let's finish up the class by answering the biggest, most frustrating fluid mechanics questions you all are asking on engineering forums right now. We scoured the internet to find the overarching themes and recurring disasters you are struggling with in the field. Question number 1, and we see variations of this constantly. I have a new industrial cooling loop. Why do my system's pipes vibrate violently and bang during the morning startup and evening shutdown, but run totally fine, smooth, and quiet for the 8 hours in between?
Based on everything we've covered, this is a textbook classic symptom of unsteady flow in water hammer. During the 8 hours of steady operation, the flow is stable. The velocity and pressure aren't changing, so the forces are balanced.
But during morning startup and evening shutdown, massive centrifugal pumps are spooling up or heavy isolation valves are opening and closing. You are creating a sudden, massive shift in the momentum of the fluid mass.
That massive kinetic energy of thousands of gallons of water starting or stopping is instantly converting into violent pressure transients that travel as acoustic shock waves through the piping network, literally physically shaking the pipes.
And what is the actionable advice for fixing a system that's already built?
First, audit your valve actuation times immediately. Implement slow-acting motorized valves wherever possible to extend the closure time and allow the pressure waves to cancel out. Second, strongly consider retrofitting variable frequency drives or VFDs onto your pump motors.
Instead of a pump slamming on at 100% speed instantly, a VFD electrically ramps the motor up slowly over 10 or 20 seconds, accelerating the massive fluid mass gently.
Finally, inspect your physical pipe supports. Proper steel anchoring won't stop the internal pressure wave, but it will physically stop the pipes from thrashing around, preventing the metal joints from fatiguing and eventually snapping.
Question number 2. How do I stop vortex shedding from destroying my sensor probes in a crossflow?
This engineer has an expensive thermal probe sticking perpendicular into a high-flow municipal water main, and the flow keeps snapping the metal probe clean off after a few weeks.
This goes directly back to flow-induced vibrations. The fluid separating as it flows around the cylindrical metal probe is shedding alternating von Karman vortices, rhythmically, relentlessly pulling the probe back and forth. If the metal keeps fatiguing and snapping, it means the vortex shedding frequency, calculated by the Reynolds number based on the water speed, is perfectly matching the natural resonant frequency of that specific metal probe. The resonance is amplifying the vibration until the yield strength of the steel is exceeded.
To fix it, you essentially have two options. Change the physical structure or change the aerodynamics.
You can change the natural frequency of the probe by swapping it for one that is physically shorter or significantly thicker. This shifts its resonant point far away from the shedding frequency of the water, preventing the destructive feedback loop.
Or, if you absolutely cannot change the required probe dimensions, you must alter the aerodynamics. You can intentionally machine a helical strake, a spiral groove, or raised fin onto the outside casing of the probe.
This physically disrupts the uniform, straight-line separation of the boundary layer, entirely breaking up the straw frequency so the vortices cannot organize into a synchronized, destructive resonant force.
Final question number 3. Why is my newly installed pump aggressively underperforming when my CAD math says it should work perfectly? The engineer calculated the required head pressure, bought the exact pump from the catalog, and it's delivering 20% less flow rate than promised.
Assuming the pump isn't defective, 9 times out of 10, this massive headache comes down to an extreme underestimation of real-world energy losses, specifically the boundary layer friction and the minor losses we covered earlier.
The engineer likely perfectly calculated the major friction losses of the long, straight pipe runs, but they either ignored or vastly underestimated the minor losses. Every single elbow, T-junction, partially open isolation valve, and sudden pipe expansion in that schematic destroys mechanical energy via turbulent viscous dissipation. It taxes the system heavily.
Or, tying it back to our earlier discussion about the viscous sublayer, they assumed a hydraulically smooth pipe friction factor from the Colebrook-White equation when they shouldn't have. They looked at a brand new, seemingly smooth steel pipe and said, "That's smooth, friction will be low."
But they completely fail to realize that at their specific, incredibly high operational Reynolds number, the viscous sublayer is compressed to a microscopic thickness. The internal manufacturing roughness of that steel pipe is protruding right through the sublayer, causing massive, unexpected turbulent drag. Textbook theory is a starting line. It is not the finish line.
Exactly. You must aggressively account for the physical, ugly reality of the installation, the exact fittings, the true Reynolds number, the actual wall roughness, not just the idealized frictionless straight-line distance on a pristine CAD drawing.
We spend so much time in engineering fighting the inherent chaos of fluid. We try to chemically suppress turbulence, we try to aerodynamically silence vortex shedding, we install massive nitrogen tanks to dampen water hammer.
But I want to leave you with a final provocative thought to mull over before we close out this deep dive. What if we stop fighting it? What if we lean into the chaos? Brilliant researchers are currently prototyping and designing bladeless wind turbines.
Instead of massive spinning fiberglass blades that kill birds and require heavy gearboxes, these turbines are essentially just tall, highly flexible poles standing vertically in the wind. They are intentionally designed to harvest energy from vortex-induced vibrations.
The engineers mathematically tune the flexibility of the structure to perfectly dangerously resonate with the Strohal shedding frequency of the wind. They take that violent, oscillating mechanical resonance, the exact same terrifying phenomenon that destroys bridges and shears off heat exchangers, and they use linear alternators at the base to turn that thrashing kinetic energy into a source of completely frictionless, highly efficient, renewable electrical power.
When you truly deeply understand the underlying physics of the chaos, you don't have to fear it. You can harness it.
If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.